To explain the structural failure of steel structures in beams and trusses and the cables. And the major modes of the failures in the beams, mainly we have bending, which is nothing but flexor failure, shear failure, diagonal compression failure, inadequate development length, inadequate spacing, change in nature, and magnetic of loads. In this figure showing that this is the beam under that condition of this major modes failures. This beam was failed. First of all, I am explaining about bending in flexor failure in a beam, which is nothing but bending is also known as a flexor failure, which is nothing but due to the overload, the simple support it sags, which is nothing but which deflect to the downward. Due to this deflection, top portion of the compresses and the bottom portion of the beam presses into tension. As a result, compressive forces are developed at the top and the tensile stresses are developed at the bottom. But in the figure is showing is the opposite to that, which is nothing but actually we have the compressive forces are developed in the top and the tensile forces are developed in the at the bottom. But here we have, due to this deflection, here we have the top portion is the compresses and bottom portion of the beam presses into the beam. Concrete itself is strong under compression to take the compressive stresses, but it weaks in tension. Therefore, the steel reinforcements or bars are provided at the bottom to take up the tensile stresses, which is nothing but concrete is strong because in the compression it takes compression weaken the tension, so that the tensile reinforcement are provided at the bottom. The section can be hovered, which is nothing but steel more than required, or it can be under reinforced, which is nothing but less than the steel is provided in that section. Among these two, under the reinforced sections are preferred for earthquake resistant point of view, because in under reinforced section steel reaches its peak value and stresses compared to concrete. This both I think under reinforced sections and over reinforced sections we considered in the earthquake resistance. Note, we can say that under reinforced sections are always preferred as compared to over reinforced and steel reinforced section. Steel began is a ductile material, yields of giving sample of a time before failure. But in case of the over reinforced section, steel is a more, therefore concrete is its peak value of stress. Earlierly, concrete can beginning a brittle metal. It does not give the enough of time to escape, but how during the earthquake. This is the in this figure is showing the beams which occur in the rupture due to that this is up this due to the occur in the deflection and under reinforced is considered in the earthquake resistance point of view. And this in this below figure we showing that corrosion of the cracks and flexure failures. And next slide is shear failure in the beam. This is type of failure in the beam occurs due to the shearing action of the forces upon them. Cracks are included at 45 degrees with horizontal area developed due to action shear. Generally, the cracks start from the bottom or middle depth and progress towards the top and bottom of the face beams. This type of failure takes place when the shear force is large in the relation to bending moment in beams. Shear action can be prevented by providing suitable designing shear reinforcement, which is in the form of three mainly types of shear failures in the beams. One is a vertical shear stirrups and bent up bars, and combination of the A and B, which is nothing but vertical and bent up bars. Vertical stirrups we can call also called as a minimum shear reinforcement, and this bent up bars we also called as a negative reinforcement. For an earthquake point of view, this type of failure damage is great importance as these cracks occur near the supports, leading to the failure points of the column and beam. This type of shear failure is brittle and must be avoided. This type of failure can be prevented by placing a shear stirrups closely placed near the supports of the, or providing a bent up bars at the distance 1/7 or to 1 by L by 7 to L by 4, where it is L is the effective span. Here we have the main three types of failures in the shear failure, which is nothing but vertical and bent up and combination. It's by this to avoiding the failure, we have to provide the shear stirrups at the providing at the at the distance of L by 7 to the L by 4, where L is L effective span of the beam. Is the types of failures in the beam. In this a flexure failure, and this is a tension failure. This is a diagonal, which is nothing but diagonally cracks will occur in that, and shear compression failure. And next one, I am explaining about diagonal compression failure. This is the diagonal in the figure is showing at the diagonal, which is crack is creating at the 45 degrees in the top, and which is nothing but in the compression zone. This type of failure generally takes place in the beams when the concrete occurs in the compression portion. This occurs due to the presence of point load. As a result, the diagonally cracks formed in this type of rocks are start from top and proceeded to the bottom. These cracks are actually will occur to the how will occurs means from the top to the bottom. Shear reinforcement is essentially provided to prevent such type of damages in beam. Colloidal provision should be strictly followed, which clearly indicates the maximum level shear stress permitted in the beam. Development inadequate the length of in a beam. This is the main point in the just number Thaudi in the RCC in the steel structures we use the code bit for calculating the development in the length of the beam. Development in a section can be defined as the minimum length of the bar, which should be embedded in the concrete behind any section to develop by the sufficient bond between steel and the concrete for the force equal to the tensile and the force developed in the bar at that section. This is the mainly useful for that for behind the steel and the concrete to give the equal forces developed in the bar section by using the length by increasing the minimum length of the bar in embedded concrete. Generally, it expressed as in the terms of diameter of the bar. Bound area in the steel bar by concrete is necessary so that it does not slip while taking stresses allotted to it. But if the bounded length is not embedded properly in the concrete, then hence chances of slip from the concrete may cause the failure of the bar, which is nothing but if not be taking the stresses in the not be taking the proper stresses in the steel or any concrete, may chances to slip the concrete failure on the membrane, which is not the bond, which is not the bond area, which is nothing but inadequate development is not occurred in that beam. Next one, spacing means the overlapping of steel reinforcement bars of joining to them increasing the lenses, which is nothing but uh, if the I'm taking example for that. I'm if having a rod 12 rod I'm taking for this, I take 10 meters for this providing for extra only 10 meters is there for the bar to using the slab, but we want another bar also, not what we can say, it's not సరిపోవట్లేదు అంటాం కదా, it's not enough to that, so that we have to add another bar by taking any 5 meters bar, so that by adding the slab, which is nothing but by joining them is meaning in that slapping. Steel reinforcement bars are usually available in the 12 meters in the market, but casting members of the length greater than 12 meters will require joining the steel bars effectively by spacing. Generally my markets we have available 12 meters, but casting is greater than 12 meters will required for joining the steel bars by spacing. At the lapping location, the bars transfers huge magnitude of forces from one another to, therefore welding of two bars is done and tied with binding wire and helps in effective load transversing mechanism. These locations must occur near the support and the tension steel as the bars can yield, resulting in the collapse. At the location of the spacing of the vertical stirrups are closely placed so the chances of the failure due to the large stresses can be avoided. This type of failure will be brittle because of steel bars do not reach the maximum stresses value due to the inadequate lap and spills, and therefore concrete fails. Next one, sixth one is change in nature and magnitude loads in a beam. Beams load should be checked for the worst combination of dead load and live load and earthquake loads. Beams are generally safe against the design dead load and live load, but due to the unexpected earthquake forces acting on them, the combination of loads increasing the main floats falls due to the values which is designed for. It becomes a mandatory for builders and the design to take the care of earthquake loads. Proper guidelines laid by down by Indian standard seismic codes. failures in the steel structure, which is nothing but in the connections in the trusses, is the most critical for the most frequent failure in the steel structure. We can design any steel member but beautifully. We can extract pieces, but due to design a joint, it becomes a tedious. This is the joint in the figure showing. You need to consider load over envelope and design a joint maximum possible force. But generally, connection fails first is case their unpretended force. Any steel member can be take the secondary load because their material is uniform and casted as single piece. But joint behaves a brittle fashion and takes some predicted loads, but not all of it. This is a wonderful steel structure, and we can construct beautiful appearance for that. But this is for due to the joints we need more forces, so that reason we not getting the joints not getting the proper forces by doing steel structure. So due to that joints only the steel structure maximum will fail occurs in the connections. Now the joint above can fail because of the failure of number of balls or weld length that we decide. Underestimating in the calculating the values can lead in the failure. uh, I can say we can say that what we can say that the we think as that of balls and the weld length we decide as a failures will occur, but not but not this is the wrong calculating than that we lead the failure by calculating only. I remember one old saying for this kind of failure: one bolt is no bolt. I was told by one of the professor that while designing a connection, even if the forces are such that one bolt can carry the tension or the compressive loads easily, you should place two balls at that connection. Seems quite different, but it gives a thought. It seems logically and wise to use balls. The thing is the a structural design you can design a perfect and just use a one ball for the connection, but the construction is not in your hand. The ball material is not in your hand. Accidents are not in your hand. They are a random, and now certain probabilities associated with this. Probabilities are added to increase the probability for the failure of structure. Suppose you have applied a one bolt and you knows the one bolt going connected to actual life will be weak or have rusted there. There is a possibility. So always better to apply two balls in one place of single ball. But when you require six balls, you may do not make seven. It will be logically. Now I'm knowing that what I am telling about. If one bolt is no bolt, if one bolt is required, which is nothing but we make it's due to the weak or a rust, which may occur so many problems for that, so that we have to use the two balls for that if they're using a single ball place. In case of welding, all you know that is to check the weld length, but there again you need to conservate in the providing the weld length, because while welding is generally connected on the site, the connection is brittle and should be carefully designed. This is the failures in the beam. Textual failures occur in the beams in bending, or you can say that when the lateral loads on the beams increasing, which is nothing but lateral limit is nothing but breadth or depth wise, we can say that, or by comparing to this lengthwise, this breadth wise is the shorter. Is limit kind of failures take place, but this one of the least occurring failure in the steel structure, because of we have a too straightforward formula. We can say need to see that section will satisfy criteria, but is the one important failure will occur in the laterally torsional buckling, and this is the failure in the compression. And next I will show the one slide, important slide, which is the buildings with columns in that. When I'm saying the one interesting one fact by the Charlie Chaplin. Charlie Chaplin is blocked in the stick. Due to that, I'm showing the another slide, the video of this how the will occur.
That's the nominal condition. So this is pinned. This means that if I push and cause buckling, the ends have not translated. There's no motion this way, but there is rotation. The ends are allowed to rotate as if they've been pinned. So that's a pin-pin boundary condition. If I were to take a similar stick and clamp it so the ends could not translate and they couldn't rotate, they had to stay horizontal, it gets a lot harder to buckle. Right? Essentially, a clamped column in compression acts like a pinned column and buckling that's shorter than it really is. For clamp boundary conditions, K is more than 1 or is less than 1. So that goes up. Right?
We can say that by using that, by interesting fact, this Charlie Chaplin is the famous most character in history. You can always find that in within stick. But wait, we have ever seen this stick when he rests on it. The stick is pictured in the above is describing of the one most fundamental characteristic of the column in the field structural engineering called buckling of the column. But why did the buckle? What made the stick to bend instead of taking the load straight down the ground? Well, here we're discussing about the event. Buckling is called as unstable occurred in the structure because of excessive loading. In 1757, mathematician Ledon Lunar derived a formula for calculating the maximum load for by slender column. But we do have a mean by slender when the longitudinal dimensions of the member which greater than the cross section of the member. That is called as a slender member. You remember you should use the word slender describing the compression in column, not where the any tension. This is the slenderness. This is what you can say lunar equation, which is nothing but lambda L effective by under root I by A by A. This equation describing the slenderness ratio and the limit slenderness ratio of column varies in the material changes. For example, steel column is said to be shortened if the slenderness ratio is less than 50. And these all are the equations for the to finding the buckling, why the bucklings will occur. And this one of the article we focus in the steel columns because the steel is very high and leads to similar cross section of area member to resisting a particular force as the compared to concrete. So the problem of the buckling generally arises in the steel columns only, not in the concrete columns only. This picture is showing the buckling of supported simply supported column. Load B is on a column from the straight configuration is more buckled configuration. Now why did move? Because till now we learned that axial forces are directly transfers the force without any instably. Every statement is a universe has a got stages of the equilibrium, and the statement will give the former minimum possible load. Consider the system in the figure. I'm showing in the figure the deflection in the system very or small. The column is slightly buckled. Now if you take the equilibrium of the buckled shape of the column, you find the load required the buckle. The column is less than the load actually carried by the full cross section. And failure in the tension I am explaining. This failure occurs in the stretch. And one second, here we say that Euler's formula column will break when the load reaches the value of critical load. But when Charlie Chapman rested on the stick is buckled and it did not break. Why? It's so that it's not strange. Well, we assume that deformations are small and the denominator of the curvature equation. This is in fact we come up with a result buckling load in the profile of the buckled column. So we can't say that whether column is arrive effect or not. They might no think of that find out answer by of Charlie Chaplin's case. This is the answer using the theory of elastia. We consider that higher order of differential equations and working. We not it. On doing this, we can actually find the profile buckled column at a particular load. This theory is elastic enables to use the answer of the buckled stick Charlie Chaplin. We can use to calculate the elastic. We find the calcium still can carry 15 to 20 more than loads, which means that buckled column requires nearly 1.2 p, which is not load of to fail it completely. This is the interesting fact this today I am telling you. And the another point fourth one is tension. In in this kind of failure, the member is yield first. This is the necking phase comes into the picture and fails reduced cross section. This leads to very high strain energy. It takes large amount of load to fail the membrane in the tension. But wait, this is a mystery over here. There are two more failures in the tension. We probably will not think about. One is the block shear failure, and another is a net section rupture. This happen in the near in the connections only at the Ashra engine node catchments by designing above tension. This is the net section rupture. In the figure is showing elastic stresses and alternate stresses in the net. When we design a tension member, we check that the cross section of area is sufficient or not, particularly force. Let's just say area is A. Now here the correct connection, we create a bolt hole. In the figure is showing the bolt hole is created in the, so the area of member reduced, the particular location is shown in the figure. Let's we consider the area of a location of the bolt hole B 0.9 area. We can check that the area is sufficient. Applied a load, find that load is exceeding the member will fail at the location of the bolt hole is called as a net section rupture. Next one, block shear failure. In this type of failure, the complete one side of connector member come out. Gray area in the picture above, when we pull the member is generates tensor forces near the connection. The balls experience shear failures because of small section of member metal experience of shear. If the stresses are high but not sufficient to fail the member at section, they will shear apart member against some of amount tension. This is the block shear failure which is showing in the figure, which is nothing but both one two balls, which is what we can say that coming connected member is coming out, dividing into that. Next one I'm showing the local failure. This will occur due to that global level in the tension and compression or bending, but we can say that forces from the certain limit, it can be lead to some local failure, one of the most common failure. This one. And next one I'm explaining about the about failures in the cables of a suspension bridge. This occurs in this the damage occurs in the pre-stressed steel cables of a suspension bridge. The bridge is used to cross one of the most important river at that in Portugal. The main structural elements of the bridge are steel cables. Each cable is composed of 84 wires distributed by 12 plus 1 stud wires. Each of the wires has thickness between 4.52 and 4.65. All the damage part subject of the study. This wire is damaged at the bridge as a result significant of traffic over the bridge because it stopped a significant period of time. In some wires fails due to the excessive oxidation corrosion was preferred access of damage process. The cable's fracture distance identified microscopically 21 wires corresponding to all three loads winding expected ductile failure structures, which is nothing but cup cone and near beginning anchor between 100 to 250 mm. When the main cables which occur by observing the microscopically, we get cup cone failure which occur in the anchors between 100 to 250 mm. Next one, this is the showing in that cup cone figure is showing under the ductile failure. These three we showing the brittle fracture failure, corrosion and BNC are showing her arrow point. 45 wires are distance between 600 to 900 mm beginning anchor and shown in the I statement of corrosion. And brittle type of display from the end in the narrow point figure B and C developed in the various lengths, sometimes reaching the 50 mm. Thank you for giving this opportunity.